Assalamualaikum and very good morning everyone. First of all, I would like to thank all participants for joining this webinar with the title Energy Transition Opportunities and Challenges in Power System Research at TNB. This webinar is broadcasted live on IEEE PES Malaysia YouTube channel and Facebook platform. This webinar is organized by IEEE Power and Energy Society, PES, Malaysia, and co-organized by IEEE UPM Student Branch. I am Lisa from IEEE of University Putra Malaysia, Student Branch, is who will be MC for this session. Our speaker is Mr. Muhammad Khairul Nizam bin Muhammad Sarmi from TNB Research. He will give the talk on energy transition, opportunities and challenges in power system research at TNB. Before I pass the session to our speaker, I would like to inform you that if you have any questions regarding the discussed topic, you can type your questions in the YouTube or Facebook chat box. I will post the questions to the speaker during the Q&A session. First of all, I would like to invite Agung Firmansyah from IEEE PES Executive Committee for Industrial Relations and Professional Activities to introduce IEEE and IEEE PES to all of you. Agung, to you.
Um, okay, one moment. Let me share my screen. Okay. Okay. Can you see my screen now?
Yes, I can see it.
Okay. Assalamualaikum and very good morning to all of the participants who joins this webinar today. And I would like to say, okay, one moment. Okay. I would like to say thank you to UPM student branch and also to the speaker, Encik Muhammad Hairul Nizam, for being with us today. So please allow me to give a short introduction about the IEEE Power and Energy Society Malaysia. Okay. Um, okay, with the team of the PES Day team, the team is a clean energy revolution. So the mission of PES is to be the leading provider of scientific and engineering information on electric power energy for the betterment society. And then, as you know, IEEE is the world's largest professional association advancing technology for humanity. So we have a global reach of 1,000 members and countries, and also millions of technical documents, standards, and technical societies as well. And then Power and Energy Society, or PES, is one of the largest technical society in the IEEE. So 45% of IEEE standards are created by PES. Okay, what can being a membership of IEEE PES can help you? Is that can grow the maintain and your technical expertise, get connected with other professionals, and contribute to the future and power energy society. And then PES what does PES have that resources of PS that can benefit to you, which is we have online webinars, tutorials, on-site trainings, workshop, technical journals, and a series of Plan Talk basic courses for industry novice. So also the activities of PES, we have invited lecturers like distinguished lecturer program, conferences, awards for outstanding engineer, linking with industry, technical activities, final year program, and senior member drive. So for those who has some sufficient experience in being academician or in the industry, senior member is the highest member or the highest grade for which an IEEE member can apply. So the benefit of the being a senior member of IEEE is that the professional recognition of your peers for technical and professional excellence. Okay, so we have in the IEEE PES, we have also in the website, there is a online resource center. So it contains tutorials, videos, reports, articles, webinars, slides, conference slides, and many more. So resource center, I think some of them can be accessed by IEEE member, and some items can be accessed by public. Okay, so this is the PES Malaysia leadership from 1994 until now. So the current chair is Professor Hazli Mokhlis from University of Malaya. Okay, so this is the picture of the IEEE PES Malaysia Committee 2021. Okay, so with that, I would like to encourage for those who has not become IEEE PES member to join PS for the more benefit to your professional career. So in order to become a PES member, first you need to become a IEEE member first. So and then you can apply the same for the PS. So this application can be done easily through online application through IEEE website. Okay, I think with that I finished with the PES short introduction. So I pass the microphone back to Lisa. Thank you, Lisa.
Thank you, Agong, for the introduction of IEEE and IEEE PES. We hope that those who have not yet to register as IEEE member, please join us so you will get all the benefits mentioned by Agong just now. Now it is time for the main agenda. Let me introduce our speaker for this webinar. Mr. Muhammad Khairun Nizam bin Muhammad Sarmin obtained a Bachelor of Electrical Engineering from University Technology Malaysia, UTM, in 2010 and is currently pursuing a Master of Electrical Engineering at University Tenaga Nasional, UNITEN. He was with Malaysia Marine and Heavy Engineering (MMHE) as a technical executive before joining TNB Research as a researcher in 2010. He is currently the head of the Power System Unit at TNB Research. His research interests include power system stability and control, modeling and real-time simulation, and modern energy management systems. He led a team of researchers to develop advanced power system applications at TNB. He and his team have contributed to the development and implementation of the Automatic Coordinated Voltage Control System (CVC) for TNB Grid System Operator (GSO), which has been in operation since June 2016. He is also actively involved in the implementation of Wide Area Monitoring, Protection and Control (WAMPSC) for TNB. His next research will focus on grid flexibility to facilitate energy transition (ET) in Malaysia. With the introduction just now, I would like to call Mr. Khairon Nizam to give talk on energy transition, opportunities and challenges in power system research at TNB. Passing to you.
Okay, thanks, Ms. Lisa and Mr. Agung. So, Assalamualaikum warahmatullahi wabarakatuh. I'm Nizam. You can call me Nizam. I'm from TNB Research. So, thanks for joining all for this weekend session with, I think it's just a sharing session between in research and also how we can contribute to the society in terms of technology that we have already developed at the NB and would like to share things that have been done so far and in the future. So first of all, I would like to thanks Mr. Agung for the introduction and Mr. Lisa. And okay, now I'm sharing my screen for today's presentation. Okay, all right. I think this is just a sharing session, and today's topic is about the energy transition, opportunities and challenges in power system research at TNB. So, my name is Muhammad Karun Nizami Muhammad Sarmin from TNB Research. Okay. So, as the title is, where it's about the energy transition, where the energy transition is a pathway towards the transformation of global energy sectors for fossil-based energy production and consumption to a carbon zero that made possible, among others, by the technology investment in energy sectors. So, as reported by EC recently, where the renewable energy capacity mix is projected to achieve 31% by 2025. This is including large hydro generation, where the hydro generation capacity in Peninsular Malaysia is about 2,000 megawatt, and including the RE, the recently announced by the EC also, where the LSS for already in place. So there will be a more challenging to the utility to meet the target and facilitate the integration of the RE in the future to meeting the of RE in by 2025. And then with the penetration of RE increasing, then it is necessary or necessity to TNB to facilitate the energy transition. But we need to ensure the resilient and reliability of the grid operation that can withstand sudden disruption or in unanticipated system elements failure. And therefore, the advancement of power system research in grid flexibility is anticipated to be a catalyst in realizing the ET to achieve Malaysia's net zero carbon goal. So today's presentation is to share about past, present, and future research in power system in TNB. So to begin the session, I think I would like to introduce our company first, where I now with TNB Research. And the TNB Research is a research arm of TNB. It supports TNB core division in enhancing availability, reliability, and efficiency of the energy supply. So we are among the largest R&D companies in Malaysia and subsidiary of TNB since 1993. And we are not a profit-driven center of electricity and environmental research. And our specialization is in energy and environmental sector. And we are also awarded R&D status by MIDA since 1997. We have a few experts of team of experts, and we have numbers of doctors and researchers, and we also have a subsidiary, namely TNB Labs. Our research focuses in applied research and also advanced research. For the applied research, we have research in power delivery, power generation, environmental management, and strategic research. And for advanced research, we have various focus area in carbon power generation technology, emission and waste management technology, smart grid technology, and also green energy technology. So this is the focus area on the energy transition and smart grid at TNB Research. So we have a generation, focus in the future generation sources, and we have team of expert in generation area, built and environment and climate change, regulatory and environment science, civil and geoenforcement, informatics, and material group, renewable energy and green technology. And for the grid of the future, we have a team that doing research in to improve the substations and also asset performance. And another group focus on the utility automation and lightning and earthing. And power system is my unit where we are focusing on wide area monitoring, protection, automation, and control that I will discuss later. And we have another team in doing research in smart grid. And the next is the future proof regulatory, where we have four areas in built environment and climate change, regulatory environment science, renewable energy and green technology, and also smart grid. The next is TNB Labs, where TNB Labs is our wholly owned subsidiary of TNB Research that committed to being a premier total service solution provider globally. And we provide services in terms of quality assurance, scientific services, and technical services. So in quality assurance services, we provide service in terms of quality audits, product inspection, training, consultancy, services, and product certification. And in scientific services, we have lab called Expert Oil Diagnostic Services, High Voltage Testing Laboratory, and training and consultancy. And for the technical services, we have team of expert in forensic engineering group, power plant inspection, and training also. So this is the services that offered to our clients. As mentioned, we have power plant inspection, forensic engineering, expert oil diagnostic, high voltage laboratory, quality assurance, commercialization also. And we provide also services in terms of environmental and climate change, CO2 capture and utilization, environmental impact assessment, hydro optimization, materials, engineering, cables, lightning, power system, and also IEEE 150 system verification. So, and then next, let's begin our talk today. So I will start with the energy transition and the energy trilemma. So as you know, that this is people that um, I will talk about the energy transition energy trilemma. So we have three elements of energy trilemma, which is energy security, energy affordability, and energy sustainability. So this is the index that we can measure the healthy energy system, where a secure, equitable, environmental sustainable, which seen as a well-managed and balanced dilemma between the three dimensions. And the energy security is the something that capacity to meet the current and future energy demand reliably and withstand and recover swift from system shocks and minimal disruption. And the energy security is the effectiveness of management of domestic and external energy sources, as well as the reliability and resilience of energy infrastructure. And for energy affordability, the ability to provide universal access to reliable, affordable, and abundant energy for domestic and commercial use, and basic access to electricity and clean cooking fuels, and technology access to prosperity, enabling levels of energy consumption and affordability of electricity, gas, and fuel. And energy sustainability is the transition of energy system towards mitigating and avoiding potential environmental harm and climate change impacts that proactively and efficiency of generation, transmission, and distribution, decarbonization, and air quality. So I will move to the next slide where we will to talk about the grid flexibility. So as you know, when energy transition is happening now. So grid flexibility is the important role to facilitate this energy transition. So energy transition, uh, variable renewable energy is uptaking and increased rapidly in recent years. And as announced by the Energy Commission, that we are targeting 31% of renewable energies by 2025. And as we know, the VRE or renewable energy sources, such as solar, are intermittent in nature and giving rise to challenges in balancing the power system and maintaining security and reliability. And this is then to address these challenges that we need to find new ways to increase the grid's flexibility. We require innovation in the way policy makers, regulators, and utilities plan, manage, and operate the power system. So with that, the increased grid flexibility needed to manage the high VRE, a more reliable, a more flexible grid will ensure that power system will, with a large share of VRE resources, can be operated reliably and at cost effectively. And increasing flexible in the power system can come from both supply and demand side. Therefore, the benefit of the grid flexibility is that it will open up opportunities to integrate large quantities of VRE into the system while maintaining electricity supply reliability. reliability. And this can drive electricity decarbonization and help transform the whole energy sectors. And so at TNB, we are talking about the grid of the future. So what is the grid of the future at TNB? So this is the key objective of the future, where the grid of the future will have to cater for new challenges while sustaining reliability and at affordable cost. So three main component or three key objective of grid of the future that we to accommodate more renewable energy sources that is intermittent in nature, and to manage grid operation complexity where more VRE is integrated on the grid, that system will um, have to be managed to maintain its reliability, so that there is less risk to blackout. And the another objective of the grid of the future is to cater for bi-directional power flows, where we know now today there is more scheme. For example, the NAM and whatnot now introduced. So there will be a generation that the power generated at household. So, for example, today we can see more panels installed at home, and in future maybe there are EV cars that can charge and discharge to grid. So it will become the V2Gs, but in the this maybe happen in the future. But this is something that we as a utility to prepare for all this and intelligent grid. And vision of the future is the grid digitalization and modernization. And this is to achieve a stronger, reliable, and flexible power delivery system by latest power system technology and digital infrastructure. So to increase this flexibility, so we need to have uh, elements such as interconnection between region, and as Malaysian interconnection or TNB interconnection, we have connection or interconnection with southern Thailand through HVDC interconnection, and to Singapore power system with AC system. And this flexibility also requires a demand side management or demand side response, and power electronic and flexible AC transmission. Maybe we can manage or control the new controllable loads, and the flexible power plants control, where we can maybe curtail the power plant during the emergencies, and also the rest curtailment. So rest somehow, if it can in emergency situation, that we need to reduce or curtail the output, the generation of the rest, then this is something can contribute to the flexibility of the power grid. And 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 storage is another key element in grid flexibility, where it can provide a source. It can become a source or sink to such as, for example, to maintain the grid frequency or provide services in terms of frequency response during the emergency or intermittency of the renewable energy. And the other elements is about the electric vehicles, where, as I mentioned just now, the electric vehicles maybe in the future not only charge, but it can discharge to the grid as a V2G. So the framework of the grid digitalization is to have a two-way communication and advanced digital infrastructure, where we use real-time application platform. This is the innovation that we did through research. So we come up with the a device called real-time application platform that we can use it at multi-layers of in the power system, uh, and we can connect at the to the sensors. So as the real-time middleware. So sensors, for example, we have PMUs, phase measurement units, IED, intelligent electronic devices, remote IOs, input outputs, and so forth. So, and we also have another layer called real-time application. So here we have application that runs in real time. So we can do data filtering, conditioning of data, and then pass to the filtered data to the upper application operational layer. So the data can be used for load forecasting, unit commitment, outage management, and also for real-time application. For example, real-time contingency analysis, real-time security enhancement, general control, and vote file dispatch. And we can have a closed loop system by providing from the sensors to the actuators, where we can have the wide area management system and control, that we could have the grid monitoring, analytics, and management and control that can send and detect the power system in case there's something happen in the system or events that can lead to uh, uh, emergency situation. So we can finally send the control signal to the power system to execute the remedial actions to mitigate issues in power system. So with that, I would like to continue with the research in power system at TNB or TNB Research that we have started or already in place, and also what we can do in the future. So uh, let me begin with this program where we call it Wide Area Intelligence System, or WISE program. This program started in 2007, and a few programs or few applications that have been developed since then. So this is the program that utilizing phase measurement unit, PMU, application, and therefore we can use it for monitoring, protection, and control. So few applications that we have developed, for example, line thermal monitoring, and power system, power oscillation monitoring, real-time voltage stability monitoring, adaptive auto-step protection scheme, advanced overload protection scheme. And all of this is using similar architectures where we sense the signal using phasor measurements, and finally a signal is sent back to the power system, to the actuators, to mitigate issues in power system. And after that, since 2013, we start to embark other application in energy management system and control. So we started with coordinated voltage control system, where we develop can manage or regulate the that can minimize the losses. And then we have a few more applications in terms of, for example, real-time power system analytics or or RTPSA, and the dynamic state estimator that using the phasor measurement units also. And then we have now uh, look into more uh, research in terms of what we can help to facilitate the energy transition. So all of this has lead to the new research and that we can provide the grid operation with a more flexible. Right. So this is what I've said just now. So we have developed a called CVC, or coordinated voltage control system, that a three-tier voltage control architecture operating the control is at the grid system operators control center since 2016, with just a Suntas area, or we call the TNB Central Area Network. And only then, now we are at the phase two, where we integrates more grid elements, for example, generators, transformer, tap changers, shunt capacitors, and reactors, or the grid voltage. And as shown by this we have three key namely tertiary voltage control (TVC), and secondary voltage control and primary voltage control. So the TVC provide the optimal reference voltage of the pilot buses using optimal power algorithm, and with the objective function to minimize losses. And the secondary voltage control coordinates voltage control devices within the control zone and provide the set point to power plants and control signal to reactors and control region. So, and voltage control, where it's execute control commands from the control centers, and the generator and transformer and capacitor and static power is control to meet the to minutes. So all this is need to be done in a slow manner. So every that issued by the central server be remotely controlled by the at the power plant, and also the and reactors and transformer tap changers at substation. This is how we so we rest the now the power plants and the transformer tap changers to meet voltage requirements. And and a power network or power system where with the adaptive domain or control zone, we can split the power system into several control zones. So we do this is because, as you know, the voltage is regional problem or localized. So if we know the boundary or the weak couple of the network, then we can split virtually of the power system to maintain each region's voltage, and this can be determined or can be performed uh, with the each real-time work, or we call the state estimator from the energy management system of the control centers, and we perform the basic and will provide TNB will provide the reference to each for regulating the uh, generates and to meet the objective uh, of minimizing the system losses. This can be performed in the time range of 1 to 5 minutes. And then finally, each region consists of its own control devices, in power plants, for example, the generators, and in our CVC in the now integrating the large-scale solars that to contribute the voltage of the power grid. So that with as you see, it will provide the reference sets of reference to the power plant, and the power plant will be with the high voltage reference and regulate will regulate its voltage and this perform a range of and and the connection is back to the uh, server to monitor the uh, the is so any controls that executed from CVC, then we can monitor how it's performed in terms of system losses. So another, if we can see at the right hand panel here, we can monitor the performance of the system, the healthy of the system. So we monitor the condition of the application running at background, the communication signals and whatnot. And I move to the next, our flagship. So this is called real-time hardware in the loop simulation. So we have the lab and the capabilities in our lab that we can simulate the grid in real time using digital simulator, real-time digital simulator. And it's capable of simulating large power system network for demonstrating the smart grid ecosystem. And we can model, for example, if not only the power grid, but we can model grid components, for example, the DRs and the energy storage, and also the virtual devices, for example, the RTOs, phasor measurement units, IEDs can be models. And we, as the the system is operates in real time, then we can interface to external devices, the physical device. And for example, as you can see here, we have phasor measurement units, the control devices, the power amplifier, and we could also have the network emulator that we can emulate the 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 network, uh, and and we have the external system. Here we have the historical data that can be stored in the server, and real-time displays, application server that, for example, we use the CVC to evaluate its performance. So all the application that we develop, we can integrate to the real-time hardware in the loop simulations uh, to see how does the CVC perform in real time before actual deployment. So we have a device, as I mentioned earlier, we have a device called real-time application platform. That this is the enabler of the system where this real-time application platform can interface uh, or can be the gateway of the application and the physical devices or grid elements. So in this example also we have the SCADA front end to emulate the SCADA system. So all this completes like the actual environment. So this is uh, the platform that's very useful for us as a research institute. So for each R&D develop, R&D solution developed, so we can verify it in the laboratory before the actual deployment. So, um, all right. So, yeah, in current research, we are looking at uh, demonstrating the smart grid ecosystem with layers of smart grid architecture, including the components, its components, smart grid components, communications, functions, for example, demand response, virtual power plants, and other businesses application. And this can be used as a digital twin. For example, one of the example is the connected voltage controller, as mentioned just now, and we can have a digital twin for other application that installed at the grid. Uh, for now, we have special protection scheme, SPS, that has been implemented to protect the grid from large disturbances. So that can be part of the digital twin, where every applications that before we do actual deployment, so we can test it in the lab to verify its performance, and to to uh, to head off any problems before it's occur, and prevent a downtime. Because for the real time application that performs or execute controls to the grid, that's something a must to be verified. So we do not want to make the system that can uh, give a negative impact to the system, to the power grid. So with this platform also, it can help to improve the critical process of the cycle times, and to drive the innovation and performance by better understanding of system requirements, and develop enhancement to the existing system. So in case the example that I gave just now is CVC or SPS, so special protection scheme that currently deployed in case we need to do the extension of the system. So uh, it can be retest again in the lab, and as the system verified, then we can do an actual deployment. So this is another interesting topics where we are uh, researching in wide area monitoring, protection, and control. That this is somehow can be used, or has the ability to sense or analyze, learn, decide, and respond to changes in the system. And currently, we are focusing on the voltage and thermal security. So in the future, we will include more application such as stability, transient stability, and voltage stability to be part of this WAN pack. So this is the architecture of the WAN pack that we developed. So we use the real-time data stream from the linear state estimators, RTUs, PMUs, and feed with the models of power system, and the contingencies list to be processed by the analytics engine that analyzes the contingencies, securities, static securities, voltage stabilities, transients, and provide the control action table to the WAN pack that can be executed by this WAN pack to uh, mitigate the issue at the power grid. So WAN pack has the ability to detect the occurrence of event and execute the controls that provided by the real-time power system assessments tools. So I think I need to go quickly since the time is running out. So the next is the recently developed, which is linear state estimator. The linear estimator is a state estimator that used only PMU measurements to provide the best estimates of the power system state, and it's a linear estimators that process after the conventional state estimation, the state estimator. This is the how we the framework of the linear estimator. So the first stage here called conventional state estimator that uses SCADA measurement and do a bad data detections, nonlinear state estimations, and provide the state vectors of the power system. And then the outputs of this conventional state estimator is used by the linear state estimators. And the linear estimator received PMU measurements, and also the measurement will passes through bad data detection, linear state estimation, and finally produces the solution by linear state estimator. This is the another framework of the detailed framework of the LSC. And one of the example of the LSC that we perform in the lab with the real-time simulator just now I showed. So uh, here we have multiple PMU measurement in the substation, and we have the state estimator output in the blue lines here. So as shown in this figure, that the actual value of the or the true value of the state is very close with the linear estimator output or value. So it shows that the estimator can accurately estimate the true value of the system state. So in the next, as the topics is mentioned, so it's about the energy transition. So more distributed energy sources, more renewable energies. So as we in power system, we uh, need to look more in terms of research to facilitate the energy transition. So uh, currently we are started or embark in modernizing the grid technologies or infrastructure. So another element that we need to look into is the energy uh, resources management system, where this GRMS can organize and intelligently manage the growing number of grid edge resources added to the electric grid, such as rooftop solar, energy storage, and electric vehicles. And the GRMS need to manage demand response, use centralized generations, energy storage, enabling virtual pipeline. So I would like to mention here that in TNB and TNB Research, we has embarked on a project, namely virtual power plant that utilizing energy storage. So we have selected 4 areas to be installed with the energy storage, with the capacity of 250 kilowatt up to 500 kilowatt. And this is a pilot project to demonstrate the feasibility of the virtual power plant. And we have also conducted feasibility study for demand response. So this is the elements that will contribute to the flexible grid in the future. And for the DRMS, so it will enable DR such as solar PV aggregation, disaggregation of solar in forecasting. So as the solar PV is a downstream the output of the solar PVs that unobservable. So this called disaggregation of loads. So um, we can measure the powers, the load at the substation level, the PMU level, and we can maybe through analytics, so we can disaggregate between load and solar PV, so that we can know how much is solar generation at the downstream. And with this technology, the real-time application platform technology, we plan to use application that can help to integration of the DER or renewable energy sources. Right. So I think I towards the ending of my presentation today, and now it's about 1 hour. So this is our team of experts. So this is our lab facility, and Opalati is back over there. So right. So I think I can pass back to uh, Miss Lisa to continue this session.
Thank you for an interesting talk. On behalf of the organizing committee, I would like to thank Mr. Khairul Nizam for the very informative talk. I believe all of us understand the main points from the talk just now. Now, I will proceed with Q&A session. I will read the questions from YouTube and Facebook comment chat box. So for the first question from Nur Ashida Salim, is there any possibility for academicians to collaborate with TNB in any of the research area mentioned? If yes, how do we initiate the collaboration?
Okay, good question. So actually, we have done several collaboration with universities, not only limited to Unitan as our university, the Tenaga universities, but we also do more collaboration with the other university. So I think we, as a start, we can have maybe as a collaboration in terms of we need to uh, see what area that we can jointly research in. So and can perhaps have uh, s- uh, I think some agreement or things that we can start to work together. It's possible.
For second question from Samir Ahmed, my question is to get reliable grid operations, the synchronization of various power generating stations, how important it is.
Yeah, good question, because this is I think about the stability of the power system in terms of transit stability or rotor angle stability, when we talk about the synchronization of power grids, power generation. So uh, this, if we can't manage it properly, so we'll create a massive impact to the grid. For example, in the last 1996 event, where there is a large disturbance at the eastern corridor of the power grid of TNB. So it creates the generation synchronization was lost during that time. So makes the power grid unstable until a total blackout happened during that time. So this is one of the area that our interest, where we are, as I presented just now, we are uh, we have research, we have embarked in research in wide area monitoring, protection, and control. So with that, with the technology, we can monitor the health condition of the power grid in real time, mainly with the phasor measurement units. And from that, if something happened in the power grid, for example, there's unsynchronization of the power generation due to the loss synchronization, or the instability, the transient stability due to a large disturbance, then with the one pack, we can quickly isolate the area that blackout or scale blackout. So this is still at the research state. So we still need to do more R&D. So our grid system operator, or a national control center, is now also look into this. So how we can have a more flexible grid with wide area monitoring, protection, and control, so that any disturbance that happen in the grid can be mitigated.
Next question from Feng Xin. Does TNB research team to any internship students?
Yeah, of course. Internship at TNB Research, you can, I think you can log into our website, and I think there's a section that you can submit your application for internship. Um, undergraduate, but also for masters and also PhD. So please log into our website.
Okay. Next question from Mariana Wyman. Do you have any plans to install PMUs in the distribution grid and run LSE or hybrid SE for distribution circuits?
Yeah, thanks, Mariana. So this is a good question, and I think each utility in the world is investigating whether PMU can benefit distributions system. So this is one of the area that we are looking at right now. Yes, the answer is yes. We have planned to install PMUs at distribution grid, but uh, we for start, I think the research is to see what value can we provide to the distribution system. As you know, the PMU currently, the price of the PMU is not cheap, and of course the price is going down, and maybe in next coming years we can deploy so-called distribution PMU, where a more compact and cheaper PMUs for distribution. This is to make PMU viable. Of course, we know the benefits of the PMU, but due to the high price of PMU right now, is maybe still need to be justified to be installed at the distribution level.
Next question from Samir Ahmed. Can we use your research for imposed electric tariff?
Um, uh, I'm not so clear about the question, but uh, I think since our research is currently focusing on for the transmission, the high voltage. I think if we can use our application at the distribution or consumer level, then it could be used to impose electric tariff. So if I'm not sure if this answers the question, but if you have further question more, you can maybe clarify or ask me later.
Next question from Agong Firmansyah. With the development of grid control system by TNBR, how long is restoration time after a total grid blackout occurrence can be expected?
All right. So with the grid control system, mainly wide area monitoring protection and control that I presented just now. So this is a tool that we are looking to prevent blackouts or a total grid blackout. So before, since Mr. Agong is asking about total blackout, so the system is trying to prevent the system blackout. So I think uh, uh, the answer is yeah, before the system blackout, then we uh, uh, already makes the system else condition uh, back to the normal condition. So um, okay, if the system requires to uh, isolate a partial or area of this power system to prevent the total blackout, then the area maybe takes some time after the system stable, then before it's synchronized back to the grid. So if the with the WAMPAC, we can quickly mitigate the problem, and then after a few minutes, perhaps we can reconnect the isolated area from grid to be synchronized back.
Next question from Muhammad Lutfi Othman. It is possible to use the OPA-LRT if collaboration is possible. We don't have HIL experiments to validate our findings in protection scheme we are working in. We have visited your lab before.
Uh,
I think this is from
Thanks.
Dr.
Yeah.
Lutfi.
Yeah, thanks, Dr. Luffy. So I met Dr. Luffy, I think few times, 2-3 times. He already visited our labs. So thanks for the question, and thanks for visiting us, visiting our labs. So it's possible we can we can have a collaboration. So we also would like to know what the university is doing. So what's application we can use, for example, as I presented just now, we develop a few real-time application that can help to ensure more resilient and reliable power grid. So if university has this similar application that has intention to work with our team, for example, to use the opolarity, then I think it's welcome. So we can discuss and have this opportunity to collaborate with the universities. Yeah.
Next question from Ida Hish. How do you incorporate the state estimation data or measurements in long-term planning?
Yeah, as you sees in my presentation just now, so we use the estimator for the input to the real-time application. So it's not being used for planning. So, however, if this state estimation, because with this linear state estimator, we can produce a more accurate state estimates, then we could use we could use to we could use it for planning purposes. For example, we can use it so-called uh, uh, what is it? The snapshot, right? So for we can take a snapshot of the power grid at a certain time, so we can have expand the network for planning purposes. For example, we can include uh, in the snapshot. For example, currently we don't have large penetration of renewables, and we would like to see what's the impact of renewables energy in 5 years time or 10 years time. So we can use that snapshot of state estimator and expand it and include more renewables in the snapshots, so we can do planning for mid-term or long-term studies.
I think that's all the question. I think that's the last question. I would like to thank Mr. Khairunizam for answering the questions from the participants. With that, we have come to the end of the program. I hope all of you could support all of our upcoming events. Please follow the IEEE PES Malaysia Facebook, Instagram, and YouTube channel. Also, IEEE UPM Student Branch Facebook. Stay safe everyone and Assalamualaikum.
Okay, thank you everyone. uh, Selamat berpuasa. Assalamualaikum.
Thank you.